Okay, so here the ASK modulator is given, right, as ASK modulator. But looking at this, it will be difficult for us to understand that what is actually happening inside. So I'll try to make our own ASK. And I would like to tell you that in the ASK, actually what we have, we are having a product modulator, digital product modulator, okay, that will multiply your message signal with the carrier signal. The message signal will be digital in nature. I told you in the introduction class about the categorization. I told you that if you can remember, then on the basis of the carrier signal, if we have the continuous wave sinusoidal signal, then we can have the amplitude modulation and angle modulation. And if we take the digital side, then we'll have ASK, FSK, PSK. And on the basis of the train of impulse, we have the pulse amplitude modulation, right? And on the basis of the pulse modulation, pulse amplitude, pulse width, and pulse position. And so basically, last class when we have taken the pulse amplitude, pulse width, and pulse position, please concentrate on this point. So last class we have completed pulse amplitude, pulse width, and pulse position. So you might have remember that time the carrier signal was train of impulse, right? So you have to keep this categorization into mind. What I am telling you now, you please concentrate on this, and if possible, you can note down these things. However, I have already discussed those things in the introduction class also. We have three types of modulation. First, we have the analog modulation, in which we have the amplitude modulation and angle modulation. And in the angle modulation, we have frequency and phase modulation. Here, your carrier signal and message signal both are a normal analog signal. However, the message signal is random in nature, and carrier signal is a sinusoidal signal, continuous wave sinusoidal signal. Both are analog in nature, right? This is first group. In the second group, we have pulse modulation, where your message signal is any random analog signal. Message signal is any random analog signal, and the carrier signal is train of impulse. Okay, train of impulses. And in the same category, we have aligned the delta modulation, adaptive delta modulation, and all those things, right? Or pulse code modulation. So for all of them, if you see, we have the random analog because random message signal is always of random behavior, that consists of so many single frequency signal, but it is an analog signal. And we have the train of impulse that is of very high frequency, and that we have taken as the carrier signal. And your third category is this digital modulation we are going to start today. So there we have the ASK, FSK, PSK, then QPSK you may have, and QAM. Now QAM is for both the AM and this and the analog and digital both, right? So I'm not talking this one about today. I'm just talking about ASK, FSK, PSK, QPSK, okay? QFSK is also there. All those things, the digital modulation. Here, your message signal is digital in nature. Okay, this is very special. The message signal is digital in nature, but the carrier signal is continuous wave sinusoidal signal, high frequency sinusoidal signal. So you have both the digital signal and the analog signal. The message signal is digital in nature. There's always random, obviously, because you don't know what will be the signal. So that will be a random signal, but that will be a digital signal. And your carrier signal is a high frequency sinusoidal signal, right? Is it okay? Any query regarding this? Okay. So first we'll start with the ASK, amplitude shift king. So here we have to take a product modulator. So what you can do, if you want to make a product modulator, you can make yourself also. I told you, I guess after amplitude modulation, we have done the product modulator DSBSC. So there we have used the product modulator. So you can use that one. Or else for this particular experiment, you can take the multiplier also. So you have a multiplier, and you have two input for this. Obviously, one is your message signal, right? So that have to be a digital signal, a random digital signal. So what we can do, we can take the signal what is taken here. Okay. So I've taken the same input signal. So what is this? This is some random symbol. Okay. And if you want to see the behavior of this random symbols, first of all, you should know what is what is the nature of the massive signal what you have taken. So the symbol rate is one symbol per second. So inverse of this one will give you the frequency. Okay. And four symbols has been taken. So four symbols means what? You have four labels. You can see this is first label, this is second label, and this is third label, and this is fourth label. Now here you know that that the digital signal should be of, you know, it should have two label only, right? Which one are those? The higher level and the lower level. So we have the higher level and the lower level. Now if you can see, we have from 0 to 1. 0 to 1 means what? It is a unipolar symbol. However, the digital signal, when we are saying 0 to 1, so it is actually the symbol, right? It may have any voltage value like 0 to 5 volt or 0 to minus 5 volt, like that, or 5 to minus 5 volt. But here we have taken 1 volt. Okay, we can take 1 volt, we can take 5 volt, we can take any value. But by taking this value, actually it is giving us the appearance of the unipolar. That's why we have taken from 0 to 1, right? And there's no harm in taking this one. So if we take 0 to 5 volt also, it will have same, but it will always show 5. So that's why I have taken 0 to 1. Okay. This is the behavior you can see, right? So this is the input signal. Now, if you want to improve the symbol rate, so we can make it we can take 5 symbols per second. So this is the 5 symbols per second value. Okay. So now we have this random signal that is having 5 symbols per second and 5 symbols per second. Okay, so you can evaluate the frequency per second. Per second means what? Time is in the denominator. So this is the frequency only. And the amplitude is from 0 to 1 volt. Okay, this is the input signal you have taken. So this is the massive signal we have taken. Okay. Now next we have to take the carrier signal. Okay. So I would like to show you something regarding the carrier signal also, which I want to discuss with you long back. So suppose we have taken the signal. Now see, we have a signal of say 1 hertz. Here it is 5 hertz. So it is of high value. Let's say if our carrier signal value is less, if our carrier signal value is of lower frequency, let's say, then what will happen? You can see what is the meaning of that. You have wide time period, you can see. Okay, wide time period. Now if I'll make it of 5 volt, then what will happen? So if I'll take it of 5 volt, here then you can see, okay, at the transition phase we have some same value, but we know that it should be of higher value, isn't it? So if we make it say 20 hertz, I don't know whether the system will support or not. Yes, it can be supported by the system, we can see. So this is your master signal and the carrier signal. This is the difference between them in the time scale. This is not modulated signal, just the carrier, the message we have taken. Now, if I'll modulate the signal, this master signal with this carrier signal, then what will happen? So now you can see the effect. The effect is that actually you can see, to make it more clear, I have shown you like this. You can see that here basically when you have input as 1, okay, when you have input as 1, you have the carrier signal, that is the modulated signal actually. And when you have input as 0, you don't have the carrier signal there. This line in between, what you can see, this is the reference line actually, reference line. So I'm going to remove this master signal once again just to give you a better view. So you can see that actually you are going to transmit this signal. You are going to transmit this signal. So this signal says that the at the receiver end, the place when you have 1, you will have the modulated signal, and when you don't have the when the value of the master signal is equal to 0, that time you don't have the carrier signal. So ideally the receiver will not receive anything. Only noise, if something will be there, will be received by the system. So it means what, the receiver will be able to understand that when I'll have the something, some input, okay, when I'll receive from the transmitter side, that means it indicates that the input, the value is 1. If I'm not going to receive anything, it means that time that the input is actually 0, right? So 1 and 0. So this is actually the output of the amplitude shift keying, which they are trying to show here also. But here they have, in your example, they have tried to show you two voltage levels, because they have taken the ASK value of 4 steps, which is practically not correct, but because practically it should have only 0 or 1. Okay, 0 or 1. So is it okay? Any query, anybody?
No, sir.
This 0.5 why I have added, because nothing, it is not having any role in the modulation, because modulation line is this one only. This just to show you that it is just to make it align with the massive signal. You have already seen that. If so don't get confused. We can see that here, just by putting this value, we can see that actually it is starting from this line, so that it can cover from 0 to 1 value. If I'll remove this 0.5 addition, it is just a clamping, okay, clamping of the modulated signal. If I'll not use this one, then what will happen? It is not going to change the meaning of the modulation. But since we are looking to this on the common plot, so then it will be difficult for us to verify. Then what will happen? It will appear like this, okay. So to make it appear like the master signal as the envelope of the modulated signal, okay, this clamping has been done. This don't have to do anything with the actual modulation, okay, just for the visualization purpose. So I suggest you to please take the snapshot of this. This is the snapshot of the modulated signal along with the master signal. And you know what you have done? Nothing. You have just multiplied the carrier signal with the master signal. Okay, you have a high frequency carrier signal. You have multiplied this one with the master signal. So this snapshot, I guess you have taken. And this is the diagram. Please take a snapshot of this one also. This random symbols we have taken here. The frequency is 5. That is 5 symbols per second. Okay, and we have to take 2 symbols. And the carrier signal we have taken of 20 hertz, amplitude is 0.5 volt, and it's a cosinusoidal signal. Now here I would like to tell you one more thing, which is very interesting and important for you to understand. When we go through the theory of ASK and PSK, then we have gone through so many things. Okay. About the ASK, it's simple. We start with ASK always, and we say this very common line that when the massive signal is present, then you will have the transmission of the carrier, else there will be no transmission of the carrier, which you have just now analyzed. Now, if you come to the FSK, I'm not going to discuss FSK at this moment. First, I'll discuss PSK because there is a similarity between ASK and PSK, and then we'll go to the FSK. So in the PSK, phase shifting, it says that whenever there is a transition, okay, transition means from 1 to 0, like here at this position, okay, or from 0 to 1. So at this position, you can say transition from 0 to 1. So whenever there is a transition, right, here there is a transition from 1 to 0, here 0 to 1, likewise 1 to 0, and here 0 to 1. So whenever there is a transition, okay, from 1 to 0 or 0 to 1, there is a phase shift. There is a phase shift of 90 degrees. A phase shift of 90 degree means at that particular instant of time, okay, this is the instantaneous value. It is not like you will have to wait that when this particular signal will terminate, will complete its period, and then it will change its phase. It is not like that. In the cycle, okay, in the periodic cycle of the signal. So at any moment when there is the transition from 0 to 1 or 1 to 0, so that particular instant of time, the carrier signal will shift its phase by 90 degrees. Previously, it was showing the cosine behavior. It will show the sinusoidal behavior. If it was showing the sinusoidal behavior, it will show the cosine behavior. It means what? If for 1, it will showing cosinusoidal, then for 0, it will represent the sinusoidal. Again, when 1 will come, it will show cosinusoidal. When 0 will come, it will show the sinusoidal behavior for the same frequency. For the same frequency, right? So there, actually, what we have to do. So actually, it is not like cosinusoidal to sinusoidal that we try to understand. That's why we are saying this thing. Actually, there is a phase shift of 180 degree and changing its phase by 180 degree and making it cosinusoidal to minus cosinusoidal. Previously, it was cosinusoidal, then we have minus cosinusoidal. What does it mean? It means that whenever there is a transition, we'll multiply the carrier signal with 1 or minus 1. Actually minus 1, because previously it was with cosinusoidal. We'll multiply it with minus 1, it will become minus cosinusoidal. Again, when transition will be there, that is means from 0 to 1, it will go back to its previous condition. So for that, again, we'll multiply this with minus 1. So minus 1 into minus 1 will be 1. So we'll have the cosinusoidal signal. So it will actually oscillate between the cosinusoidal, minus cosinusoidal, and minus cosinusoidal. So actually, what we have to do, we have to simply multiply it with 1 and minus 1, like that. 1 and minus 1. So then what we have to do, we'll make, now the symbol labels are 2 from 0 to 1. If we'll make it from minus 1 to 1, let's say we have multiplied to 1 and minus 1. So then the carrier signal, cosinusoidal signal, whenever there will be transition, it will be multiplied by that value. Now we are going to see that thing. What does it mean? Now symbol value we have taken 3. Okay, so 3 steps will take. So now it will go from 1 to 0 to minus 1, like that. So we have actually 1 to minus 1 value, you can see. If you see this one, basically we have the values. Okay, 3 values we have. But then there is a problem. The problem is that it have to go from 1 to minus 1. It should not wait in between at 0 value. Okay, so we have to make it going from 1 to minus 1. So it is again having 2 symbol period, right? 2 symbol period, but that 2 symbol period should go from 1 to minus 1, like that. It should not be in between 0 to 1. Okay, so then what we should do? So what we can do, we can add here some value so that it will show its variation. Okay, so how we'll do that? Yes, yes. Please ask if you have query. Yes. So what we'll do that we'll add, sorry, we'll subtract basically okay. So this is one way how we can do it because our purpose is to make it bipolar. So going from minus zero point 0.5 to zero point 0.5, that means going from minus 1 to 1. This is one way. And another way is that we can change the source also. Adding this thing may sometimes confuse you that what should be the value we have to take in. So instead of taking the random symbols, we can have other options available here to represent the same thing, and we can go for the. So we can take rectangular pulses. You can see here the higher level is 1 and lower level is minus 1. So actually you have to do the same thing. Okay. Previously we were taking 1 and 0, and so we have to multiply the signal, carrier signal with 1 or 0, and now we have to multiply with 1 and minus 1. That is the only difference. Okay. So let's say we have taken this particular input. This is the input. Okay. So I know that it feels that you are dealing with the very periodic pulse. So you can change the pulse also whenever you want, right? But at this moment, for understanding point of view, we have taken this particular one. You can change the duty cycle here also. In place of 50%, we can make it like anything else, like 30% we can make. So in that case, it will be having this behavior. But still, you can see the variation is that here the on off time will change. Okay, on of time will change. So to make it to improve the appearance, we can make it for 50% only, or sometimes when we have the real input, we can do with that. So whatever it is, we have to just multiply. You can see this bipolar signal, okay, with the in this carrier signal what we have. So now no need to take it 20 hertz since we have the 1 hertz signal only. So we can make it 10 hertz also. Okay. And we can make amplitude also of 1 volt because the master signal amplitude is also 1 volt. One more modification is required is that no long we read these pulses and all those things. In its very basic form, we can use this because both are having same intensity. Okay, so if I will show you a magnified view of this one. So for that, I'll take the value from 0 to 3. Now you can see this particular, or even if I'll make it from 0 to 1 instead. Yes, so you can see here the change at the transition level. Okay, there's a phase shift of 180 degrees. Okay, at this transition stage. Again, if you go from the next change, for the next change, you can see the change here also. Right? So you can see the change at the transition phase when it is going from 1 to 0, that is 1 to -1, that is upper value to lower value, and then from lower value to upper value. Whenever there is a transition from upper layer to lower layer, you can see the change here. You can imagine, you can understand. Okay. Now you can see, you can feel that the change will take place at this moment. Now I would like to show you that the change may occur at any place whenever there will be transition. So instead of 10 hertz, if I'll make it say 15 hertz, for an example, let's check what will happen. So you can see now the changes in between. This particular section of the pulse or the signal actually have not completed its cycle, and in between it encounters with the change, and so it have to the phase shift of 180 degree has been applied here. So you can see here, likewise here also, right? So in this complete one cycle of the carrier signal, whenever it meets with the message signal, when there is a transition, okay, from 0 to, sorry, 1 to -1 or -1 to 1, it will immediately at that point only, it will reflect the phase shift of 180 degree. That means it will be multiplied with -1 value. Okay, you already know the constellation diagram, right? So you know that. So that we'll talk about when we'll deal with the QPSK. So right now we are talking about the PSK. First we'll discuss with the FSK and then we'll go to the QPSK, right? So you have seen that basic difference is that in the amplitude shift king, we were using the unipolar system. It was from 0 to 1, and we have multiplied the carrier signal with that, and we have the ASK signal at the output. Now in the PSK, actually, we are multiplying the carrier signal with the bipolar signal going from 1 to -1, and we have a phase shift of 180 degree at the transition point, right? Any query from anybody? Please let me know. Yes, I'm expecting some good queries from your side. If you have any query, please let me know. Anybody? Don't hesitate and don't keep your queries with you. Ask if you have to discuss anything. Next, we have the FSK actually. So, okay, first you take the snapshot of this one. This is your PSK. Please have a snapshot of your result. is take the snapshot of the design. And this is the specification for the massive signal. And this is the specification for the carrier signal. We have taken 15 Hz co-sinusoidal signal of 1 volt. Okay. So now we are, yeah, anything from anybody? Any query? Okay. So now we have to see the FSK. Now I told you the problem with the frequency modulation, that for that we need a system where the input of the carrier signal, that is the frequency of the carrier signal, we can change by the control signal, and control signal is nothing but the master signal. But that provision is not there in the COMSIM. Okay, for that we need the voltage controlled oscillator, and we should go for the multi-sim. Okay, but yes, FSK block is given here, so we'll use that one. But what is the idea? The idea is that we have a normal co-sinusoidal signal. Okay, so what we'll do, the carrier signal will have some frequency and the phase it will have. So we won't do anything with the phase. We just keep the carrier frequency omega, and here we'll use like control signal, VCO type of thing. So what we'll do, that will vary the carrier signal. How will vary the carrier signal? Will add a delta value to this carrier signal omega. So what we'll do, we'll have equation like cos of within bracket omega, that is the 2 pi f omega, plus delta into dt. Now delta is what? Delta is the amount of change you want to apply, and dt is the massive signal. Okay, dt is the massive signal. Here you can apply both the unipolar or the bipolar, right? So now please concentrate on this point. If suppose you are taking the unipolar, then what will happen? It will go from 0 to 1. So if you apply 0 to 1 unipolar system, then for 0 it will be cos of omega plus delta into 0. So delta into 0 will be 0. So you will have cos omega only for unipolar. And for 1, there will be omega plus delta. So there will be change in the frequency, right? So frequency will increase. That means time period will decrease. Okay, time period will decrease. Frequency increase means time period will decrease. They will come closer, right? So for unipolar system, the equation will be for higher value, high frequency, for lower value, low frequency. Okay, or there is no change in the frequency. So likewise, for bipolar system, it will be omega plus delta and omega minus delta for -1. That means for high frequency, higher value, for lower value, that is for -1, lower frequency. So in the bipolar system, the only difference is that there will be change in the frequency in both the condition. The carrier signal is not going to be same. Okay, either there will be increase or decrement in the carrier signal. But in case of bipolar, unipolar, the carrier signal will not change in case of 0, and carrier signal that is at the lower value, and the carrier signal will, the frequency will increase for 1. Okay, so that is your FSK. So that provision, as I told, we don't have any function in which we can apply the change of frequency. VCO we have to use, and for that we should go to the multisim. So here we are using the block which is given, okay, in the system. So you can see that we have the FSK modulator block. Okay, FSK modulator block, and we have the random symbols. So random symbols are actually here 4, but we have already seen that it should be 2, because 2 will show either the unipolar or the bipolar. So we can take the rectangular pulses also, and we have this 500 hertz, and frequency we have 1 kilohertz, right? So we can take a lower value also. So this FSK is of frequency, and C frequency spacing is given. Spacing is what? That delta value. Delta value is the spacing. Okay, so if we make it like 10 hertz, and the variation of 2 hertz only if we take, okay, That means for lower frequency, say it will be 10, and for higher frequency, it will be 12 hertz, like that. Okay. So now we'll run. So first of all, we will not see all those inputs which is given. We'll try to collect our own input. It's not shown here. So no problem. What we'll do, we'll take our own signal source. So we can take the rectangular pulses also here, or we can take the pseudo random code. Okay. So rectangular pulses we have taken same what we have taken in the last class. Okay, last in the last example of PSK, actually PSK, and we have to take the FSK modulator. So we'll take the FSK modulator here. We can see that we have the complex FSK modulator. So I told you that whenever we have the complex system, then what we have to do, we have to take the complex to real and imaginary converter also, right? So that is the mathematical tool. So we have taken the complex to real and imaginary converter also. We have to take higher value. So 10 hertz we have taken, and frequency spacing we have taken 2, that will give you the delta value. So this is the output for 1 hertz rectangular. Now we are going to use the pseudo random.
Sir, you are not audible, sir.
Yeah, please wait a minute. I'm actually, first I'll design, then I'll explain. Okay, so now you can see, first of all, we'll see the plot. The change in the frequency you can observe easily, right? I'll try to see a better view of this one. So if I'll make it from 0 to say 3, maybe. Okay, we'll make it from 1.2 minus 1.2 to 2. Yes, so this is the better view. So here you can see that the carrier frequency we have taken as 10 hertz and the delta value we have taken as 5 hertz. Okay, so when and we have taken the unipolar signal, you can take see it is going from 0 to 1, right? So when there is zero value, 0 into delta will be 0. So you have cos omega t, that is cos of frequency value is 10. So accordingly you will have the signal and there is no change, right, in the carrier frequency. But when you will have zero, sorry, when you have the value, say minus sorry, one is there. So 1 into 5, right, that delta value is 5. So you will have 10 plus 5, 15. So 15 hertz, that means increment in the frequency. So obviously the time period expansion you can observe. So for lower value, you can see that time expansion, and for the upper value, there is no change in the carrier signal. So this is your frequency shift king. Okay, frequency shift king, where the two frequency represents the upper value and the lower value. So please have the snapshot of this one. This is the FSK output. Please have a snapshot of this one. This is the snapshot of the design. Please have. So here this 0.5 what we have added after complex to real and imaginary and invert this is what, this is the clamping operation we are doing. We are doing the clamping operation. Okay. Just to feel that the carrier signal will go inside the same dimension as maintained by the master signal. Okay. Is both can go up and down like that. So to maintain that thing. And the complex FSK modulator, that's why the demodulator we have taken accordingly. Complex to real and imaginary demodulator. Okay. So you want to see the specification. So this is the random symbols we have taken of frequency 5 hertz. That is 5 symbols per second. So per second means frequency, obviously 5 symbols per second. 5 hertz. FSK modulator lower frequency is 10 hertz and frequency spacing of 5. So it will run between 10 to 15. Okay, 10, 15, 10, 15 like that. And the amplitude is of 0.5 volt. The complex FSK. So this is your ASK, FSK and PSK we have discussed. If you have any query, please ask. Anybody, please, if you have any query, please ask. Let me know. And to extract this one, what we have to do, how to extract the master signal back from this one. So you can see that actually we have the variation in the frequency, right? You know that thing, there's a variation in the frequency. So so if you want to extract the signal, obviously you should use the bandpass filter for frequency modulation or for FSK also. The decisions should be on the basis of the pass filter. So if you'll take two band pass filter, okay, let's say we have taken two band pass filter, okay. So we have to take the filter. So we'll go to the filter, we'll go to the IR filter, we'll see the band pass filter, okay, the band pass filter we are having. We'll take two band pass filter, okay, and we'll take the frequency of this one should be that it will allow either the higher frequency component or the lower frequency component, okay, accordingly. So so the higher frequency component if we have to take, so that is 15 and lower one is 10. So if we take for 12 to 16 to 13, okay, and for this one we'll take say 11 to 8. So it will respectively allow at any instant of time either you will have 1 or 0, right? So if it will be 1, then it will be having 10 hertz that will be passed through 11 to 8 hertz filter, and if it will be 15, then it will be passed through 13 to 16 hertz filter. Here, what I want to do actually, what I am doing. So here, first of all, you can see that yes, we can see that we are able to extract the signal back, but to make it to give you a better look, uh, I just want to make some arrangements. So what I am going to do, I'm actually going to add point 5 here, right, to for clamping purpose. Already know what we have to do. I'll add point 0.5 to this one, first of all. So you can see that, like here, when you will have one, when you will have one, you have this green signal, and when you have zero, you have this blue signal actually dominating one, because continuity will be there. So that's why you can see the small values, and it's of very small amplitude, if you can see, right? Why? Because this green one, the filter value, as per the filter value, the green one represents, you can see the green one represents 8 to 11 hertz, and 13 to 16. So this green one will allow the low frequency term to pass, okay, and 13 to 16 will allow the high frequency term to pass. So especially if you see this particular region where we have this one continuous one, so here you can see you have the high frequency term, right? 13 to 16 is the high frequency term, so you can see easily. Now, after applying the logic circuit, we can convert it into the digital form. But here you can easily identify in this region the one and the zero, right? So for the demodulation, we require the filter. So by using the suitable filter of particular cutoff frequency, you can have the correct output. Now, if I'll change this frequency because I want just a 10 hertz signal to pass, right? So if I'll make it going from 9.8 to 10.2, let's say. Okay. And likewise here also we want 15 hertz signal. So if I'll make it 14.5 to 15.2, let's see what will happen. So actually this small value variation is not possible with the software. So we have to take a good bound. So the previous value what we have taken was better. So if we have to take 15, so we should go from 13 to 16. That's the best option, right? And for 10 hertz, it have to be 8 to 11. It will give you the better result. So here you can see, like in this particular region, Where you have 0, you can see we have the green color dominating one, and for this one we have the blue color dominating one. So you know this blue color is from 13 to 16, and this green color is for 8 to 11, right? You can see. So 8 to 11 will allow the lower frequency term, that is 10 hertz signal to pass, and 13 to 16 will allow 15 hertz signal to pass. So by using the proper filter, we can extract our signal back from here, right? So which is shown here also by using this one. So that's how we can have our FSK operation, frequency shifting, modulation, and the demodulation. Yes, once again, I would like to ask you, if you have any query, please let me know. Okay, if you don't have anything, now we are going to perform the QPSK, because we have already done the PSK, right? So in the QPSK, what we have to do, you already know that we required some random symbols. So instead, we are going to take the rectangular pulse. Okay, because here I'm having option of 1 and -1, and I want the bipolar signal for PSK. Okay, so duty cycle I am going to change. For this I am taking the duty cycle of 0.6, different from 0.5 or 0.4 even I can take. Okay, and what will be the behavior, you can see. So this is the behavior. Okay, and we'll take another one with duty cycle of 0.6. So we can see we have non-overlapping symbols, right? Now here I would like to tell you one thing. Also, I'm going to make some changes that I'm going to change the start time also. So I'm going to make it start time of 0.2. Okay, then let's see what will be the change. So now you can see there is a change between the two inputs. Now about the QPSK, you know what we have to do. We will have two. We have the master signal. Okay, we have the master signal, a stream of master signal, stream of bits are there. So from that, on the basis of the position of appearance, okay, on the basis of the position of appearance, we divide it into two categories of odd and even bits. It's not like we have the 1 bit or 0 bit or 1 or -1. No, we have a train of symbols, random symbols, because we have the master signal. Let's say our input is 1 1 -1 1 1 -1 -1 -1 1 1 1 -1 1 1 -1, like that. So on the basis of the position of appearance, means first of all we have 1, then we have 1, then we have -1, then we have 1. So the first bit is 1, so it will go to the odd position, and second bit is 1, so that will come to the even position. Third bit is 1, sorry, -1, it will go to the odd position, and 4 bit is again 1, it will come to the even position. So we have 1 -1, the odd, and the even we have 1 1, like that. Okay, so on the basis of the position of appearance, we'll divide the group bits into two group of odd and even. Okay, now odd symbols like here will be multiplied by the cosinusoidal signal, and even one will be multiplied with the sinusoidal signal. Okay, and then we'll add them up. So what we have done, we have taken two, see, we have taken two symbols, you can see here, the odd one and the even one. Okay, odd and even. So we have a continuous bits, and by the help of the demultiplexer, we have divided into two groups. Okay, here let me check. Okay, so here we will first take the random symbol. Okay, pseudo random random symbol. So you can see we have the random symbol. Okay, uh, we can take from value for we say two. So this is the random symbols we have. Now our job is to make two groups of odd bits and even bits. Okay, so what we can do here, we'll take this random symbols. We'll go for the demultiplexer. Demultiplexer will have to start. Well, I am looking for one particular block, so you will have to wait for a minute. Basically, I'm looking for the demultiplexer. I found demultiplexer, but the thing is that uh, there uh, it is showing error. Okay, and it is actually not separating the. I have taken the serial to parallel, and it's not converting. So I'm looking for that. Okay. So here we can see that we have input signal. Okay, it is of bipolar behavior that is going from -1 to 1, right? And why we are taking this one? Because we are talking about the QPSK, and here we are actually going to add two PSK, okay, for odd place of bits and even place of bits, and then we'll sum them up. And at the receiver end, we'll again try to extract the signal back, right? So what we have done, we have taken the demultiplexer, which is available here with the name serial to parallel converter, because in the demultiplexer we have say 1:2 input. If we'll take then we'll have one input and two output will be there. So basically we have the serial to parallel converter. Okay, so we have used there, and to maintain the synchronization we have taken the same clock for both of them. Okay, and the bits per symbol, if you say see, this is also same. Bits per bit rate, bits per symbol is also same. Okay, so we have taken now. This is the, you want to measure the behavior, if you want to see the behavior, it's going to be like this. And now next stage is to multiply this with the carrier signal. So sinusoidal signal of 10 hertz frequency or maybe 20 hertz frequency. Okay. Now here basically, if you see, we have this type of output. So that is difficult to understand. So here basically the purpose is that we should have two group. Okay, and the instantaneous position we have to add. Like if say for the odd bit we have one, the even bit maybe one or maybe -1. So if the odd bit will be one, then we'll have cos of omega plus cos of omega. We have two cos of omega. And if we have the maybe -1 and 1, okay, then accordingly the vector sum will take place. So we have to get the complex type of output for the QPSK, and we cannot predict the things in advance. We should have the, for that, if you want to do the analytical thing, we have to do the vector addition. That is one thing, right? But here, what I am finding that this serial to parallel, it should give two stages, okay, two stages. So that error it is showing, actually it is not able to show two stages, that it should be, it have to be able to show. So anyhow, and for this we have the other options also possible. So what we can do, we can take the rectangular pulses, two different, or what we have started, of different duty cycle. Okay. And then we'll try to modulate them. Yes, madam.
बोल रही हो मुझे?
Hello.
हेलो, हमको कुछ हमसे कुछ पूछ रहे हो क्या?
नहीं 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 madam.
ओके ओके.
Then we can multiply this one with the sinusoidal signals. Of say frequency 10 hertz sinusoidal, and here the cosines. So you can see that one is going to be multiplied with sinusoidal signal, another one with the cosinusoidal signal, and we are going to add these two. Okay, so we have assumed that if suppose this is the upper one is the bits of odd position and this is the bits of even position, so bits of odd position can be multiplied with the sinusoidal signal and even with the cosinusoidal signal of same frequency, right? And they have the phase shift of 90 degree because we have sinusoidal and cosinusoidal signal. So then this will be the output. Now this output is actually here. It is the sum of the output of the odd position and the even position. So if I would like to show you the response, so first of all, I would like to show you that this actually one by one we'll see. This is the odd bits and the modulated output of the odd bits. Okay, odd bit and PSK modulation 1. Okay, modulated version of PSK odd bit position, right? PSK. So you can see whenever there is a transition, there is a PSK, right? You can see from 1 to 0 and then, sorry, 1 to -1 and from -1 to 1. There is a change of 180 degree. So we have seen just now the odd bit modulated position. Now see this one is the even bit modulation. Okay, even bit modulation, you can see this is the even bit modulation. Okay. Yes. So this you can see the even bits, okay, showing by pink color and the modulated signal, right? You can see this. Now, so we have this even bit and odd bit modulation separately. You can see the even bits and odd bit separation. Okay, you can see for a better picture, I would like to show you like here. Will give you the better picture. So here this is the separate odd and even bits. Okay, modulated signal. Okay, modulated odd and even signal. Now these two signals, red and blue, are going to be added. Okay, we'll add them up as an output of the QPSK. So instantaneous position, the bit position for the signal position for particular time instant is going to be added. That is the instantaneous addition will be there, right? And so we'll have now you can see this yellow color represents the even modulated signal. This blue color is showing the odd modulated signal. And this red color is actually showing you the QPSK output. That is the sum of that. So we have PSK odd, we have PSK even, and we have the QPSK. That is the sum of the 1 and 2. Okay. So this you can see here. This is the basically QPSK output. Finally, this is finally this is your QPSK output based on the PSK1, PSK odd, and PSK even, right? So this is your, so here you have to understand that first we'll apply the demultiplexer to separate them on the basis of the odd and even position. And then finally, we are not going to apply the multiplexer. The multiplexer will be applied at the receiver end. Here we have just added them normally at the position of appearance. Okay. So it is a normal algebraic addition of the two signals, right? The odd and the even PSK. This will transmit at the receiver end. And for the demodulation, we'll do nothing special. We'll apply this with the, if you can see, we'll take normal same carrier, because you know for the demodulation of PSK, what we have to do, we have to multiply the received signal with the same carrier, right? And then we'll allow them to pass through the the band pass filter, and then we'll apply the multiplexer. Okay. So we'll take the signal, we'll take the multiplier. So here we have our multiplier. This is the multiplier one. We'll take our modulated signal, we'll multiply with the multiplier one, sorry, the carrier signal one. On both the side, we are going to do the same thing. QPSK is a very different type of modulation scheme because here basically we are applying the time position of processing, right? So that we are applying the multiplexer and the demultiplexer. So here what I have seen to show you the response, you can see that whenever we have one and whenever we have the -1 value, so accordingly the variation you can see, right? So here we have now till now we have not applied the demultiplexer. It is the added performance, and that's why we can see this type of performance. So this is for the odd bit position, and likewise I would like to show you for the even bit position also. So see, this is for the even bit position again. So you can see the 1 and the 0 position, and accordingly the variation you can easily and you can easily verify, right? So anyhow, you have seen all the aspects. Now I would like to show you that actually we have done the demodulation, and for demodulation what we have to do, we have to take the output signal, this output signal, okay, and we have to multiply this with the same carrier signal, 10 hertz sine and cosine. So what will happen that the sinusoidal section will demodulate the sinusoidal section only, because it will then allow the lower frequency term to pass and will not allow the higher frequency term to pass. So we'll apply the band pass filter or the low pass filter, both will work. Okay. And finally, we'll again do the multiplexing, right? So when we'll do the multiplexing, it will give us the signal back. So demultiplexing, yeah, multiplexing is not required because we have not done the demultiplexing, but we have assumed that we have separated on an even position. So those odd and even positions are here only. We have already demodulated and have shown you, right? So after that, this thing is required. Your analog to digital converter is required to get the same signal. But that thing we have just now seen that we are able to extract our message signal back. Okay, just now I have shown you, right? Once again, one example I will show you. Okay, so we can see here the demodulated signal, okay, and the modulated one. Here the thing is that we need the logic circuit to represent this demodulated one into the to show the things in the same digital form, right? So this thing is left, but we can see actually here that we are able to extract the signal back, right? Here some time shifting is there, that I already told you that time shifting and the amplitude variation is always allowed, because it depends on the amplitude we have taken for the master signal and the carrier signal. First thing. Second thing, we have taken the master signal directly, and the demodulated signal is coming after modulation and demodulation. So processing time for both of them are different. So this thing is always allowed. The thing is that we can see that we are able to extract our master signal, the same periodic behavior after the demodulation. So what we have done actually here, we have taken the signal, and on the basis of the odd and even position, we have divided them into two groups. We modulate them with the same carrier but maintaining a phase shift of 90 degrees. At last, we add them up at the deep, and then we'll transmit. At the receiver end, we'll demodulate with the same carrier, respective 10 hertz sinusoidal and co-sinusoidal. And the filter will have to apply, because it will allow a particular frequency signal to pass, only the massive signal that will be modulated through the sinusoidal signal and the co-sinusoidal signal. You know, cos A into cos B will be cos 2A, or cos, 1 plus cos 2A and by 2, or 1 minus cos 2A by 2 respectively. So that will allow 1 into massive signal component to pass, and cos 2A will be high frequency signal that will be filtered out. A normal synchronous detection method that we have applied for the DSBSC case, right? So same thing will apply here to extract our massive signal back. Now, since it is a digital modulation technique, so at last we require the logic circuit to convert the analog output into the digital output, right? So that is lacking here because of this software limitation. First thing, that serial to parallel is not working here. Okay, there is some issue, and so we are not able to define in that particular way, right? But anyhow, we can see that it is giving you the nearby response what is expected. So this is your QPSK. So today we have discussed about the ASK, FSK, PSK, and QPSK. If you have any query, please let me know. Yes, Neela ma'am, are you available here?
Hello, yes.
I have completed
Hello.
ASK, FSK. Yes, I told that we have completed ASK, FSK, PSK, and QPSK. And
yes, I was thinking that you were explaining everything. So they will have to just whatever waveform they have.
Yes, they can take the
Screen share
snapshot. Yes.
They have taken a snapshot.
No, they should take. This is that diagram. I am trying to make it on the single screen.
Dr. G.K. Mishra.
Now they can take the
Hello.
snapshot. Yes, ma'am. Yes, ma'am.
Yes. I have asked them to submit 5 simulation experiment on all of them. Some of them have submitted, many students.
Okay.
But those who have not submitted, I have given that today they will have to submit first 5 experiments of simulation.
Okay.
So those who have not submitted, then yes, please take care. Okay.
Okay, students. So as Neela ma'am have told, and some of you have discussed with me also, so I want to make this thing very clear. देखिए, आपको जो है अपना एक फोल्डर बनाना है, उसमें अपना नाम और रोल नंबर की इसे आप सेव करोगे. काफी सारे लोगों ने किया भी है, और आप अपने सारे एक्सपेरिमेंट को उसी पर्टिकुलर फोल्डर में रखोगे, ताकि हम आपका वो जो फोल्डर है उसको एक्सट्रैक्ट करके देख सके कि आपने क्या सबमिट किया, और अकॉर्डिंगली द मार्क्स विल बी गिवन टू यू, असाइन टू यू. एंड अबाउट रिगार्डिंग द फॉर्मेट, तो मैंने पहले जो एक्सपेरिमेंट नंबर 1, 2, 3 दिया था, तो उस फाइल में तो आपको अप्लाई करना नहीं है, पर वो फॉर्मेट आपको यूज करना है. तो फॉर्मेट वही रखना है और आपको फोल्डर में अपना फोल्डर का नाम बना के उसमें ही आपका जो जो लैब मैनुअल आप बना रहे हो उसको उसमें डालना है. I guess it's clear. So anybody having any query regarding anything, please let me know. Neela ma'am is also here. I'm also here. So if you have any query, please ask.
Sir, could you please upload the hardware manual, sir?
हार्डवेयर मैनुअल किसका बचा हुआ
Yes,
है?
yes, we are
Sir,
going
किसी
to
का भी
upload.
upload कीजिए.
नहीं, हम लोग नहीं अपलोड किए हैं.
Okay, ma'am.
Hello, Dr. GK Mishra, we have not uploaded manual
Okay.
for hardware. We will upload it.
Okay, Vibha ma'am is also here. So Vibha, हार्डवेयर का क्या करना? Okay, so okay, it will take time. By Friday, we'll try to upload. Because we need to scan and all those things are required. Neela ma'am, is it okay?
Yes. Yes, is
By-
it okay? They have completed today.
Uh,
2 experiments, is it?
yes, we have completed,
Hello?
na, ma'am. Yes, we have completed
Yes,
experiment number.
I am telling they have completed 2 experiments today. You please go through the serial students. I am telling students, please go through the list of experiment. You have completed 2 experiments. Sir has explained everything. So you have completed 2 experiments. So altogether 7 simulation is over.
Yeah.
7.
Ma'am, excuse me, ma'am.
Yes.
Now we did the 9th one, ma'am. 10th one is QM, ma'am, QAM, and this one is QPSK.
Yes.
Yes.
So students, I told you, today we have done experiment number 9 and 12 because QPSK, to understand QPSK, you should do PSK. So after PSK, we have done QPSK.
That's
Now
right, yes.
MS
Continuation.
next class. So it's okay.
Yes, no problem. 9 and 12 we have done. No problem. So altogether 6 remains. My point. 1, 2, 3, 4, 5, 9 and 12. Is it okay? Is it okay? I'm not getting response from other students.
Yes, ma'am.
Yes, ma'am.
Regarding hardware manual, will upload by Friday. We'll have to see the
Yes.
fresh copies actually because some in the lab somebody have marked something on the lab manual, so we have to prepare a nice copy, and then that thing we'll have to scan and then we'll upload. So it will take some time. So by Friday we'll try to upload the hard copy. Okay.
And yes,
So-
by this time you complete at least simulation. Simulation experiment you complete what you have done. Okay. Folder में submit करो.
मैम असाइनमेंट लिंक में हमें जमा नहीं ना करना था.
नहीं असाइनमेंट की जगह फोल्डर में कर दो.
यस मैम, वो कर दिए मैम.
बहुत स्टूडेंट्स ने जमा किया है. आई हैव गॉन.
यस मैम, आई हैव आल्सो सबमिटेड.
हाँ 5 ओके 5 को पीडीएफ में मर्ज कर दो. मर्ज कर दिए हो 1 to 5 जैसे हम लोग इलेक्ट्रोमैग्नेटिक थ्योरी में किए थे. 5 एक्सपेरिमेंट करके उसको एक पीडीएफ में मर्ज कर दोगे तो अपना नाम से तो एक तुम्हारा 5 एक्सपेरिमेंट सबमिट हो गया. वी विल चेक इट. फिर जितना हो जाएगा बाकी को फिर हम लोग करेंगे. क्लियर? इज इट क्लियर टू
Yes, ma'am.
एवरीबॉडी?
Yes, ma'am.
Yes
So
मैम. Yes मैम.
yes, I will go through the list, those who have submitted, and those who have not submitted, I will display in the team. Those who have not submitted, जिन लोग नहीं उसी का नाम देंगे, हम पोस्ट करेंगे. Anything to ask?
Ma'am, अब 12 का भी
और
सॉफ्टवेयर
भी कुछ पूछना है?
मैम. सॉफ्टवेयर 12.
कुछ बोलो.
मैम सॉफ्टवेयर 12 का भी लैब मैनुअल अपलोड कर सकते हैं मैम.
हाँ कर लेंगे, कर देंगे.
Sir,
Uska bhi
once
manual.
can you show me the settings of that rectangular pulsar for QPSK?
Okay. Wait a minute. See, one thing, as I told you, that for QPSK, the idea is that you have to take the pseudo random PN sequence. Okay. PN sequence you have to take from the source. You can see PN sequence. Now in this PN sequence, you have to set bilevel. Okay, bilevel. And then it will have this type of appearance. Right, some randomness will be there. Please wait a minute. Now see, some random signals will generate because our objective is to have a random signal that will go from -1 to 1. Okay, try to understand this thing also. Our objective is to have random signal that will go from -1 to 1. You have other options like you can take the rectangular pulse because the rectangular pulse will go from 1 to -1. You can go for what are the other source? I just want to show you. Random symbols you can also take. But in the random symbols, you can see here it will go from 0 to 1. The random symbols will go from 0 to 1, but you want -1 to 1. So rectangular pulse will go from -1 to 1, but then it is not random. It is very periodic. So then it is good to have a PN sequence because it will give the random symbols and it will go from -1 to 1. Right? So that's why it's good to take the PN sequence for this experiment. Now after that, you need to separate them on the basis of the position of appearance, odd and even, as I told. For that, we have the provision to use parallel, serial to parallel. Serially, the bits are coming and you have to convert it into the parallel bit to odd position and even position. Okay, so that you can apply serial to parallel, but that thing is not working here. I don't know, there is some issues, right? So then manually, I have assumed that, okay, we have odd bits and we have even bits, right? So after that, we have applied the demultiplexer and assume that we have odd bits and even bits. So this we have taken as odd bit. This you can see the upper one odd bits and this one is the even bit. Okay, and then we have taken two carrier signals separated by 90-degree phase shift and multiplied them. This is a product modulator. And then we have added them up. So we have added them. So this one, this red one is, say, this one is the modulated output. I'm showing you once. This red one. This one is the expected modulated output, okay, of the QM. I've shown you the odd output and the even output and the sum of them. So this is the, sorry, the QPSK output. Okay, so PSK odd output, PSK even output is going to be added, and we have this output. So this is the PSK modulated output. Okay, so you can take the snapshot of this one. Then to demodulate, we have multiplied the signal, the composite signal, what we have received at the receiver end, with the same carrier signal. Here we cannot apply bandpass filter. Why? Because both the carrier signal are at same frequency, right? So don't have the idea that we can apply the bandpass filter. No. So we have to apply the same carrier with the sinusoidal and co-sinusoidal behavior. Okay. So after this, it is assumed that we'll have the master signal now, and then we have to apply the low pass filter to take our master signal back. Okay, the frequency you can see of 1 Hertz, so that's why the cutoff frequency have to be 1 Hertz, more than 1 Hertz and nearly 1 Hertz. So actually 1.2 Hertz we have taken, right? So these are the output of the modulated signal, demodulated signal, which you cannot actually check if you will not compare it with the master signal. So that's why I've shown you one example of that. So all the things, if you see on the same plot, it will be difficult for you to understand. But here, little bit understanding it will give you. Right. So with the QPSK, it is very difficult to analyze every stage. Well, this is the, please have a snapshot of this. This is the demodulated signal 1 and 2 and the complete modulated signal on the same plot. And after that, we should apply the logic circuit to get the signal back in the digital form. So anyhow, digital form is just the representation. So this is the overall design. Is it okay?
Yes, sir.
Please have a snapshot of this. Okay.
Sir, we
Wait.
won't have any settings in rectangular pulses of duty cycle and all that.
So those things are not required here. It is required when we are using the pseudo random code. I told you now about all the three these things. So
Yes.
duty cycle, if you want to apply, you can definitely apply. See here the duty cycle. Here duty cycle, if you see it's of 50%. Okay. And for the lower one, duty cycle is say it is 70%. So why we have taken two duty cycles? So that we can differentiate between odd pulses and even pulses. So see here the duty cycle is of 70%. Okay. And for the upper one, it is 50%. They have to be different. You can take 30%, 40%, whatever. Just it is just the indication. Actually, because we have tried to take it, we have assumed this as odd bit and even bit. So both should not be same. So intentionally, we have taken two different behavior of different duty cycles. Okay. So this is, you can see, you can take the snapshot. This is the duty cycle for the even bit, and this is the duty cycle for the. Okay, so you have taken the snapshot, and this is the duty cycle for the odd bit, 50%. Is it okay?
Yes, sir.
Yeah. Anything else from anybody?
Sir, actually, I have been disconnected from my computer, sir. So
Okay.
can you accept it, sir?
I'm getting, what is the issue?
Sir, actually, I was disconnected from the and the lab group number 2, sir, from the system. So
Please, it was actually disconnected. Please once again, please repeat.
sir, actually, my system has been disconnected. So it
Okay.
need acceptance from the lab, sir, from the main server.
Okay.
I'm
The
from
request. I can see your request on the system. Okay, please wait a minute.
yes, sir.
Yeah, I guess I have accepted. Is it you?
Yes.
Okay.
Yes.
Okay. Well, okay. So that's all from my side today. And you should try yourself. And if you have any query, please let me know. I'm here with you.
Acha, one thing, all of students, I have updated your ERP attendance for the lab till August, September. Sorry, 17th August. So I will complete till 14th, today's including. So all of you, please check your ERP attendance. Okay.
Yes, ma'am.
So up to 17th August, I have updated and I'm going to complete for September also, including today's attendance. So all of you, please check your attendance. Okay. And if you want to say, then you can inform us. देख लोगे सब एक बार attendance lab का, ठीक है? Okay.
Yes.
Yes, ma'am.
Okay.